Hey, Miss Miklos here, and in today's lecture we are talking about how to solve both exponential and logarithmic equations. And there's really two different types of problems we're going to see today. The first is when we're going to have equations that have exponents on both sides of the equation. And in this type of problem, there's actually two different methods that we can use. The first is that I can try and rewrite each side of the equation to get the same base. And a lot of the times this might be easier for some of you, okay, if you're really good at manipulating numbers in your head and thinking of them in different ways. The second method, which we could use all the time, or we could use if we cannot get the same base, is to take a log of both sides. And we'll kind of see that in action and see what that means. The second type of equation we're going to see is one that has exponents on just one side of our equation. So when that is the case, no matter what we choose to do, the very first thing I need to do is isolate the exponent. Okay, so I'm going to get whatever's being taken to the power all by itself first. And then we really have two different methods. We could take a log of both sides, or we could use the definition of a logarithm to change it from exponential form into logarithmic form. And I know a lot of you guys have been wondering, why the heck do we need to know logarithms if it's just exponential form? And we will see that when my variable is in my exponent, that's when changing it into a logarithm can be very helpful in actually solving the problem. So number one, and there is a note handout. I'm just choosing to do it not on the note handout, but feel free to download that if you want, is 4 to the 3x equals 8 to the x plus 1. Since I have exponents on both sides, the first thing I'm going to try and do is see if I can rewrite 4 and 8 to the same power. So I know that 4 is really 2 squared, so I have 2 squared to the 3x. And I know 8 is 2 cubed, so I have 2 cubed to the 3x. Now when I'm taking an exponent to a power, I know I need to multiply, so I get 2 to the 6x power equals 2 to the 3x plus 3 power, because I had to distribute that 3 to both terms in that binomial. So now that my bases are exactly the same, I can go ahead and set those exponents equal to each other. And now I'm going to solve for x. So when I subtract 3x from both sides, I get 3x is equal to 3. So x is equal to 1. And just like last chapter, we do need to check for extraneous solutions. And this is something that we can kind of do in our head. So if I'm substituting 1 in, I have 4 cubed, which is 64, equals 8 to the 1 plus 1 power, which is 8 squared, which is 64. So I know x equals 1 is my answer. So this is one method that we could use to do this problem. Now I'm going to go ahead and do this problem again using a different method. So this time what I'm going to do, I'm just going to start by what we call taking a log of both sides. And I really can use any base I want, but it's kind of that philosophy that whatever I do to one side of the equation, I can do to the other side of the equation, and it keeps my equation equal. And this is when some of our properties become really important. We learned in our previous lecture that when I have an exponent, I can bring that out in front to become a coefficient. So I'm actually going to write this as 3x times the log of 4 equals x plus 1 times the log of 8. And we know that log of 4 and log of 8 are actually just decimal values that we're going to have to figure out in our calculator. It is important for us to know, though, that we should not round until we get our final answer. So we definitely need to take our time And make sure that we are leaving values like in our calculator all the way written out. Obviously, when we write things down, I'm not going to write 10 decimals, but in my calculator, I need to keep like the exact value, and I'm not rounding until my final answer because that will change my answers if I round in certain steps. So when I put the log of 4 into my calculator, I end up getting a value of something like 0.602, and it continues, but I'm just going to write 0.602, equals the quantity x plus 1 times, and I'm going to write that as 0.903. So I know that these are kind of rounded values, and I'm leaving exact things in my calculator, but now I'm going to have to distribute. So when I do 3x times 0.602, I would get 1.806x. When I distribute, I get 0.903x plus 0.903. This actually works out really nicely because when I subtract 0.903x from both sides, I end up with 0.903x equals 0.903. To isolate x, I'm going to divide both sides by 0.903, and I end up getting x equals 1. We already checked that, so I know that that is another true answer. Now, quite honestly, I think on this particular problem, our first method was a little bit easier to use, okay? But what I will say about this method is this is something I can do on every single problem we're going to see. So it could be a good idea to use that if you don't like manipulating numbers in your heads, okay? Regardless of which method we use, we end up getting the same answer. Number 2 is very similar in the fact that I have exponents on both sides. And like our previous problem, we could use one of two methods. And for this problem, I'm just going to use the method I think would be easier since I've already modeled both methods for you. And I'm going to see, can I rewrite 2 and 32 to be the same base? And in fact, I know 2 can just stay 2. And I'm going to think of 32 as 2 to the 5th power times x minus 1. So all we did here is we rewrote 32, so it was 2 to the 5th. Now I need to think of this as 2 to the 4x power equals 2 to the 5x minus 5, because I know I need to distribute that 5 to both terms. Now that my bases are the same, I can set those exponents equal to each other. And when I subtract 5x from both sides, I get negative x equals negative 5, or x equals 5. So in my calculator, I need to double check. Is 2 to the 20th power the same thing as 32 to the 4th power? And we would see that it does work, and x equals 5 would be our solution. If you chose to use the other method, that is completely fine. You should get the same exact value though. Number 3, if we look at this, we run into some issues because there's no way I can write 7 as 2 to a power. So we may want to think back to our directions that we stated earlier about when we have a single exponent. So remember, first I want to isolate the exponent, which in this case it is, and then I could either take a log of both sides or use the definition of a logarithm. And I'm going to use both of these methods to demonstrate how we could go about doing that. So method number 1, I'm going to take a log of both sides. So I'm going to write log of 2 to the x equals log of 7. Now once again, I know that I can move my exponent out in front to become the coefficient. So I get x times the log of 2 equals the log of 7. So I'm going to have to go ahead and divide both sides by the log of 2. This would cancel out everything other than x. And I'm going to go ahead and put this in my calculator. It is important that I remember to use those parentheses. And when I put that in, I get 2.807. And I know that's a rounded value, but that is my answer. Now, for me to definitely know that this works, I need to substitute it back in. So in my calculator, what I'm going to do is I'm going to type in 2 caret, and then I'm going to do second negative. And what that does, that puts in my previous answer, which means it's putting in the exact value, not just this rounded value. And in my calculator, it does tell me that 2 to this power is equal to 7. So I know that this works. Okay, so this is our first method where I can take a log of both sides. And in this method, there's actually a variation of ways I could do it as well, because I chose to take just a log base 10, but some of you might have decided to do log base 2 of both sides, and let's talk about that for a moment. So if I had log base 2 of 2, this could become x times log base 2 of 2 equals log base 2 of 7. My 7 you can barely see there. Okay, and we've learned previously that log base 2 of 2 is really equal to 1. Okay, so whenever I have this same base and this number, if it's log base a million of a million, the answer is 1, because this is saying 2 to what power equals 2? 2 to the first power equals 2. So then I just have x equals, and using change of base, I would do log of 7 divided by log of 2, which is exactly what I did over here. Okay, so we just kind of need to be consistent in what I choose to do. Whatever base I use on one side, I have to use on the other side. But we end up getting the same answer regardless, so it's pretty open-ended. So the other way that we can go ahead and do this problem is by using our definition of a logarithm. And that's what we learned at the beginning of the chapter, when I can change something from exponential form into logarithmic form. So for example, this problem would become log base 2 of 7 equals x. So that's just the memorization we did earlier in this chapter, learning where each of these pieces goes. Now I'm going to have to go ahead and use our change of base. So I'm going to do log of 7 divided by log of 2. And once again, I end up getting 2.807 is equal to x. So I would recommend maybe doing problems in a few different ways on your homework and on your suggested problems, just kind of to see what works best for you. Okay, because I might like this method better, but you might do better just taking a log of both sides. And mathematically, they are both fine. It doesn't matter which way we do it. So I want you guys to figure out which way are you going to feel more confident in order to get all these problems correct. So number 4, I noticed that we only have an exponent on one side. What makes this one different is this is not isolated. So my very first move is going to be to move that 4 over to the other side. Now I can do this in one of two ways, and I'm actually going to model both ways once again to make sure that we're feeling okay on this. The first method would be to take a log of both sides. So I have log of 10 to the 2x minus 3 power equals log of 17. And I'm going to do two things at once here. I'm going to bring my exponent out in front, so 2x minus 3. And then I know log of 10, it really means I have a base of 10, so that means that log of 10 is 1. So I know that the left side of my equation is just 2x minus 3 equals log of 17. And when I put log of 17, remember I'm keeping this in my calculator, the full amount, but I'm just going to write out 1.230 because that's kind of the rounded value. and then I'm going to have to add 3 to it. So I would get 2x equals 4.230. And when I divide both sides by 2, I end up getting x equals 2.115. And once again, I would need to double check that in my calculator by doing 10 to the 2 times second answer minus 3, and then plus 4, and it should equal 21, and it does work. So I know this is my answer. Now the second way I could have done this is I could have taken this and used our definition of a log. So it would have been log base 10 of 17 equals 2x minus 3. Now I know log base 10 of 17 is just log of 17. And you guys will notice at this point, it's the exact same thing as this line. Okay, so my following steps would be identical to this. So regardless of which method we use a lot of the same steps. It's just the way we get there that can definitely vary slightly. Okay, so this problem, I'm going to start by getting whatever's being taken to the power all by itself. So I'm subtracting 2. And for this problem, I'm just going to take a log of both sides. If you want to choose the other method, that's great. It doesn't matter. Okay, so I have log of 5 to the x plus 2 power equals log of 23. So this is really saying x plus 2 times the log of 5 equals the log of 23. And I want to get x by itself. So yes, I definitely could distribute, but wouldn't it make more sense if I divided both sides by the log of 5 right away? And then I can get rid of that altogether. So then I have x plus 2 equals, and the rounded value here is 1.948. When I subtract 2 from that, I end up getting negative 0.052. Now obviously I need to double check this in my calculator, but when I do check it in my calculator, I see that it makes a true statement. Number 6 looks tough for a few reasons. First of all, we have fractions. Secondly, I have this number e. Okay, so I'm going to work with the fraction first. I'm going to get rid of it, okay, because why should I even work with it? So I'm multiplying everything by 3. The reason why I'm choosing 3 is because that is our LCD. So when I distribute that, I end up getting 2 times e to the 4x plus 1 is equal to 12, because we need to distribute this to all 3 of those terms. So now I'm trying to isolate e to the 4x, so I'm going to subtract 1, and then I'm going to go ahead and divide by 2. So I have e to the 4x equals 11 halves. So once again, I'm going to go ahead and I'm going to take a log of both sides. So instead of taking log this time though, I'm actually going to erase that. I'm going to take an ln. Okay, and the reason why I'm choosing to do ln of both sides here is because I know ln means log base e. So something important for us to know is that ln of e is equal to 1. So when I move my exponent out in front, I get 4x equals the ln of 11 halves. Because I have 4x times ln of e. ln of e is only 1, so that gives me 4x. So in my calculator here, I'm going to do ln of 11 halves, and then I'm going to divide that value by 4. So I get x equals 0.426. And if I substitute that in to my original equation, I notice that it works in that equation. It makes a true statement. So key thing here for us to know, we need to remember ln of e is equal to 1. The other thing we need to remember is that log base e is equal to ln. And this becomes important if I had chosen from this step, to write it as a logarithm, and using the definition of a logarithm, right? Log base e of 11 halves equals 4x. I know log base e then would become ln. Okay, so definitely it's important for us to know those two facts. So on to our last two problems, which are going to be the toughest. Shocking, I know. But this one looks strange because instead of having a single log or having it written in exponential form, I see multiple logarithms. And I notice that we have the same base here, so I'm going to recall that information we've learned previously and know that I can condense these into a single logarithm. Since this is subtraction, it would become x squared minus 1 over x minus 1. So I can go ahead and I can make x squared minus 1. I'm going to factor that into x plus 1, x minus 1, over x minus 1 equals ln of 4. And in this case, those x minus 1's cancel out. Okay, so we have ln of x plus 1 equals ln of 4. Similar to what we've done where when our bases are the same, I can set the exponents equal. If my bases are the same here, I can set these two values equal to each other. So I can actually just skip a step here and write x plus 1 equals 4, so x is equal to 3. And in my calculator, I'm going to want to check this one out. So I'm going to do ln of 8 minus ln of 2, which gives me this decimal, and I'm going to see, is that equal to ln of 4? And I noticed that both of those give me a decimal of like 1.386, blah, blah, blah. It continues. And so it does make a true statement. So x equals 3 is our answer. So this is a good example of one that we would see on our test where I need to go ahead and use our properties in order to solve this. Number 8 looks really strange, mostly because I have two things that are being taken to the power. And so I just quickly want to remind us off to the side here that e to the 2x is saying e to the x squared. Because when I'm taking an exponent to a power, we multiply. So what I'm actually going to try and do here is factor this. So I need to think what factors what factors make e to the 2x, and we already kind of said it's e to the x and e to the x. Now I need to think what factors of 2 add up to be negative 3. And I'm thinking negative 2 and negative 1. And I can use FOIL to check that I did this correctly. Now I have two different equations, e to the x minus 2 equals 0, and e to the x minus 1 equals 0. So I have e to the x equals 2 and e to the x equals 1. So I'm going to go ahead and I'm going to demonstrate two different ways to solve this. The first one, let's take a log of both sides, and I'm going to do an ln of both sides. And the reason why I'm choosing to do an ln instead of doing log, which if you chose log, you'd be fine, but I know ln of e is equal to 1. So I end up getting x equals ln of 2. And in my calculator, when I do ln of 2, it tells me x equals 0.693. Now in my second one, I'm going to use that other method of changing forms. So I'm going to write log base e of 1 equals x, or we know that's ln of 1 equals x. And without even doing any work, I know my answer here is 0. Because this is saying e to what power equals 1. And I know anything to the 0 power is equal to 1. If I plug these both back into my original equation, they both work. So this is a problem that gives us two different answers. Okay, so I know on our notes today I used a bunch of different methods. My advice would be to kind of try them out, but then choose what works best for you and stick to that when you're doing your walkthroughs, when you're taking your quiz, when you're doing your homework quiz, when you're going through all those problems. Practice what you think you will be the most successful with when we take our test.